Okay, so today's lesson is dealing with a thing called probability experiments. Now, with the concept of probability experiments, we have all these various definitions, right? One of the most important things that I want you to remember is that the outcome of something is the result of an experiment, okay? That could be a graph or a table that shows the information in a readable format. Now, the event, okay? The event is a set of outcomes with the same result. So for example, if I had two die and I was looking for the sum that's on the two die. So let's say the result of having a 4. So an event of having a 4 could be a 2 and a 2, a 1 and a 3, or a 3 and a 1. All of those are exactly the same because one dice could be one and another dice could be another, right? But you get it. You can't tell the difference. So 3 and a 1 and a 1 and a 3 are kind of the same. Now, a trial is one round of a probability experiment. Now, a trial could also be represented as a success or failure. Okay? 4 different trials. Okay? Now, we also have this new concept called experimental probability, right? Experimental probability is basically talking as the number of successful trials divided by the number of trials, i.e., in math, we would say what we want over the total. That's it. Nothing more than that, right? If you printed off my note, make sure you add this bit to it, okay? Now, let's go and fill in the blanks with the words that we have above here, okay? So those are all the definitions, and we'll see if we can come up with something, okay? Let's consider this experiment, all right? So we consider the experiment. There are 6 red balls and 12 green balls, and they're placed in a bag. Without looking, 3 balls are removed. The three balls that we pull out, we're going to say are, well, it's the result of an experiment, right? The 3 balls that we pull out is an outcome, I guess. And if the balls are the same color, the event, so this is a specific thing that happens. If I pull them out and boom, all of them are the same. That is one specific possibility, okay? So you can think of an event as one possibility. Possible thing that happens. Okay, in this case, we say if the balls are the same color, the event is considered even. If the balls are not the same color, then the event is considered odd. So this is a different outcome. Okay, now the balls are then replaced. Lastly, 50 blank of the experiment are repeated. So we're going to say 50 trials of me just pulling out 3 balls from the bag are repeated. So it's something that is done over and over again. And every time we go over it, all of the events total up to the trials. But if there are 50 trials, that's the number. If we do this 50 times, that's the number of trials that we have. And let's just finish the sentence. Are repeated and the results are recorded. The results are used to calculate basically the experimental probability of this specific event. So maybe of all of the things having just the same color, that could be a specific event. Okay. Now, let's go through these problems. So, the results of rolling two six-sided die 50 times are displayed on this chart here, okay? You notice that we have frequencies meaning how many times it actually happened, right? Each of these numbers on the bottom represents each of the different events, i.e., the sum of the two die was 2, the sum of the two die was 3, the sum of the two dies was 4, and so on up to 12, right? So when you're talking about this, let's use what we know from before, okay? So let's use the information that we have up here, our definitions that we have on our sheet, right? So in this case, it says each time you roll the die, do you get an event, a trial, or an outcome? Now, you get an outcome. So that's the result of something that just happened, okay? Now, the sum can either be 2 through 12. Each of these possibilities are called the events. So each of the unique sums are called an event, okay? So if you think about it, 1 and 4 and 3 and 2 are two different possible outcomes, okay? But they are the same event because they have the same sum. Because remember, our experiment was just to see how many times we could roll different numbers with two die. So let's just emphasize this a bit. So if you think about it, right? If you have 4 and 1 and 3 and 2, those are both events, right? And both are the same event, right? They are the same event because both of them total to 5. Both of those two different kinds of rolls give us a total of 5, and that's where we get that. Now, let's go and take a look at our next problem here. It's asking us how many trials there were. In order to figure out the number of trials, we just have to literally read this chart, okay? So I'm going to zoom in on this chart, and then we're going to figure out the numbers on the top of each chart. And we'll put the numbers on the top of each chart, okay? So you'll notice here's your chart, right? So for the first column, the first chart tells us there was one occurrence. The second column tells us there's 3, and so on. Now, basically, this chart is awesome because we call this a frequency diagram or a frequency histogram, right? And it will tell us all of the individual rolls and how many times it happened. But to get the total number, what we have to do is we have to add up all of these numbers here. So now you ask yourself, how many trials were there? So now all we're doing is we're just adding up all those numbers. So now we have 1 plus 3 and all those numbers added up. And that, from our chart, tells us we have a total of, well, 50 trials. Okay? Now, when you're looking at this problem, it asks you, see where it says which event seems most likely to occur? In this case, you're looking for the tallest bar in our bar chart. In this case, the sum of 6 is equal to 12. All right, so sum of 6 is our most likely event. Okay, now let's find the probability, the experimental probability of rolling a size of 6. So in order to write that, we're going to do this. We're going to say P of the sum equaling 6 is equal to, well, it's 12 spots out of 50. And then what we're going to do is we're going to reduce this into a fraction and then change it to a decimal or a percent. All three are perfectly acceptable for the experimental probability. So let's do that now. So in order to change 5 over 12 into its lowest form, we have to, 12 over 50 into its lowest form, we divide both the top and the bottom by 2. And we end up with our final experimental probability as a fraction of 6 over 25. Now this is perfectly acceptable for your final answer, or you turn it into a decimal by just taking 6 divided by 25 to get 0.24, which is my decimal. And then take the 0.24 and multiply by 100% to get 24%. And each of those are perfectly acceptable for our final answer for probability. Okay, so 6 over 25. So you're saying 6 out of 25 times this happened, or you can say 0.24, or you could say 24% as our final answer. So imagine I asked you to find the probability of not rolling a 6. All right. So the probability of not a 6. Let's find that. The probability of not 6. So in order to get the probability of not 6, all I got to do is look at my chart here. And I basically sum up all the numbers which don't represent a sum of 6. So that's from 2 to 5 and 7 to 12. So here's our answer. So we have 1 plus 3 plus 4 plus 5 plus 7 plus 7 plus 4 plus 4 plus 3, all divided by a total of 50 trials. Or, so that was the brute force method. Or we could have done this. The probability of not 6 is equal to, well, the number of trials minus 12 divided by 50. So how did I get that answer? What I'm going to do is I literally just say, okay, so we had our total minus the number of some 6, right? And subtract them. And then we simplify. So 50 divided by 12 is, well, 38. 50 minus 12 is 38 divided by 50. And then we can take 50 and 38 and divide both of those by 2 to get a final answer of 19 over 25. Or we could write it as 0.76, or we could write this as 76%. All three are perfectly acceptable. Okay, and now let's find the answer to the next question, which is literally an absurd question. So what's the probability of getting a sum of 13 based on 2 dice, right? 2 dice. Is it possible to get a sum of 13 on 2 dice? We're doing this question on the sheet. If you said no, then the probability of sum equals 13 is equal to 0 or 0%. Okay? Now, let's go and take a look at this last problem here. This last problem says find the experimental probability of rolling a 2 through 11, or a 12. How would we do that? Note, all the probabilities are between 0 and 100%. Okay, so when we do this, what are the probabilities? Well, we end up with 1 or 100%. And that's it. So we have all our probabilities go from 1 to a 0 to 100%. Now, so all the values go from 0 or 0% to a number 1, or also known as 100%. So when we represent those numbers as a decimal, we get 0. Okay, and then we represent 0% as 0, and then we represent 100% as 1. Okay, so now let's work on this next problem. Okay, so this is a problem, example 3. A probability experiment was designed to find the expected number of females in a family of 5 children. To simulate the genders of 5 children, a coin was tossed 5 times. Heads represented a male and tails represented a female. The experiment was repeated a number of times. The result of this is the graph that's shown here. So let's go and put the numbers for each one of those graphs so it saves us some time later. So we look at this histogram and we'll tally all the frequencies that we have here. All right, so we have 2, 7, 10, 5, 5, and 1. You know what? Let's make our life easy. So the first column is number of females, 0. 1 is a second, 2, then 3, and then 4, and then 5 right here, so we can quickly reference our graph. So to figure out how many trials were performed, all we're going to do is we're going to add up all of the numbers for each of the columns, the total frequencies of the columns. So totaling, you get 29, and we say there were 29 trials. Okay, now it's asking us what is the experimental probability. So the experimental probability of having 2 females in a family of 5. In order to find that, we just have to look along the bottom portion of our graph, which represents the number of our females, and we go to position 2, and then we go up, and that tells us that we have the following. And this is how we write it mathematically. We say P of 2 girls is equal to, well, it's just going to represent, we're getting our top number from the column, so we're going to write 10, divided by the total number of trials, which is 29, which is approximately, now I could ask you to tell it as a decimal, a fraction, or a percent. So I could write this as a decimal, so 0.34, or I could write this as 34%. So in order to get that, to go from our decimal, we just multiply by 100%, and we're done. And that is our final solution to find out the number of children, the percentage of the number of children. So now let's go to our next problem. Our next problem is asking us, it says, according to the experiment, what is the average number of females with 5 children? So to come up with the answer for the average, right, we have to figure out the number of girls, the number of families, and then we figure out the total number of girls. So for the number of girls, we have 0, 1, 2, 3, 4, 5, and possibilities of having 5 girls. So 0 through 5, right? The next column that we should have represented here are the number of families. So if you think about it, with the number of families, for 0 girls, you had 2. Then for 1 girl, you had 7. For 2 girls, you had 10. And then you had 5, and then 5, and then 0. Okay? All right, so basically, you have 0, So we have 0 girls for 2 families, right? How many total girls do I have left over here, right? The total girls is equal to 2, so 0. Okay, now for our number of girls, if there's 1 girl for 7 families, that means it's 1 times 7, which is, you guessed it, 7. For this one here, 2 girls, and if there's 2 girls and there's 10 families, that means there are, you guessed it, 20 girls. So basically the thing that we're going to do is we're just going to times those numbers to get the columns on the right for this last column. Okay, so we have 3 times 5, which gives us, well, 15. And then we have 4 times 5 gives us 15 again. And then we have, let's see, 5 girls, 0 possibilities. We're just timesing those together and we get 0. So now let's zoom in to all this information and make sure that we kind of have it all together. So if you take a look at this problem, right? We literally found the number of families, right? So the total families we know should be 29. Yeah, because there are 29 trials, right? But the total girls, is going to be, well, add up this entire column here, and you end up with a total of 62, right? So we kind of total up all the girls and then total all the totals to get a total of 62. So we just add them all up, and we add them all up. We end up with 29 and 62. So if we want to find the average number of girls, we need to take the total girls. So what we want divided by the families. Total. Now, remember, there is, for the girls, we said there are 62 girls, and for the families, there are 29 families, which gives us an approximate value of about 2.1 girls, and then that's per family. And let's move on to example 4. All right. So example 4, right? Let's take a look at it. The experimental probability is a measure of what exactly happened and may not reflect what's expected to happen. What can be done to increase the accuracy of the experimental probability? So let's say I have a coin and I flip it twice, right? Maybe I flip it twice and I get 2 tails. You would kind of expect it to be 1 heads and 1 tails, right? But the only way that could happen is if you have to realize that it doesn't represent what's expected, right? And the only way that we can change that is to do something crazy. Maybe we have to conduct more, not experiments, but we're going to say trials. So the number of times we do it has to be increased in order for us to get what we want. All right, that's it. We're done. So your homework is page 66, number 1, 2, 3, 4, 5, 6, 7, 9A. Good luck.